Today we talk about digital circuit using transistor and diode. This is the video 6 for electronics for college student. I hope you like. If you like it, you subscribe. This the more contents coming is analog circuit using transistors, and eventually that goes to the IC chip design, analog chip design, and the digital chip design. And later we talk about how to architect the CPU, everything. So the first we got transistor here for demonstration, which is this transistor. And you have to pay attention. This is not like usually. This is a collector, base, emitter. The right side face, right face. This is the left face. So 1 is collector, and 3 is emitter. Okay. And here important thing is I see how much current it can take. Maximum rating 600 milliamperes. This is pretty good amount, because usually in order to light LED you need 50 milliamp to bright one 200 milliamp. So this transistor can handle pretty good power without the heat sink. Okay, and this is the DC current gain. It's a beta, so-called beta, right? IC collector current versus DC current gain. DC current gain depend on temperature. When temperature goes up, it's increased, and operating amp. If you're operating at like a 50 milliamp and room temperature, but it's a room temperature outside, but the die inside is usually higher, like 80. So we're talking about 300, which is pretty good. The beta 300 is very good performance. You have to be careful though. This gain is before transistor saturate. Okay, when transistor is operating at the normal operating mode, that's the gain. Okay, now collector emitter, let's see, typical current here. You look at this one, DC current gain. This is translation from here. Okay, now how do you make a digital circuit using transistor? We talk about simple one. The inverter, right? So inverter, what we do is the base input, we put the switch. Okay, and this is like a large one. This is like a small 100 ohm, and in the hand-on electronics later you can see the actual circuit. Okay, and we set this the ICC is going to be this 5 volt, and when this saturate, it's a 0.2 volt, 200 millivolt. So we set, say, ICC 100 milliamp. So we can ignore this pretty much. 5 divided by 100 milli, that means what, 50 ohm, pretty small. You can set 50 milliamp, that's good enough. The reason why we set this 100 milliohm is we want to use LED. So LED is going to be here connected. Okay, now some people use LED this way to drain to the collector, and we don't recommend this because the reason is this ICC varies depending on the transistors. If you have like a 10 transistor, you connect them and drive this transistor ICC, each transistor is different, so brightness become different for each LED. Then on the PC board you have LED lamp, and this is bright, this is dark, this kind of things happen. But if you use the resistor and current flow this way, then every circuit the resistor is pretty much consistent, plus minus 10% worst case. So this configuration LED brightness is going to be consistent, so we use this configuration. So what happens is when you turn on, if you push, we do this opposite way. We wanna say when we push, it's high. So okay, when we push, then the current flow in here in the base, and that's gonna turn on transistor. So this collector voltage drop down to like a 200 millivolt above emitter, and that's not the voltage not large enough to turn on the LED, so LED is off. So the switch on, LED off. Okay, switch on, switch off, then LED is on. Okay, so this is basically we have created inverter, right? So logically this is inverter, and low high signal level is like a TTL, low high level. This is a very simple inverter we created. Now inverter doesn't have much function, okay, it's just inverted. So how do we make it say NAND? And you know the entire CPU can be constructed by just NAND, right? The NAND can be used for creating latch, flip-flop, and any other logic necessary. So single logic element is enough to create entire LSI chip, and that's, we learn about that later. There are many ways to do it. What we can do is maybe use a diode, switch, (5 volt), connect this together, okay. So what I did is one of switch is on, this is going to be pulled up, right? And the reason why I use a diode is when this voltage get high, it doesn't affect this side, okay? So it's isolated. So two input are isolated. One of them on, then this is going to be off. Okay, so in this case, actually logic is NOR, right? When one is high, then guarantee output is low. It's actually not an AND. Okay, the typical TTL input looks like this. They use a multiple emitter transistor, okay, and that goes to this inverter. So what happened is one of them go low, then this turn off. So this is a typical NAND logic component, okay? So transistor and or diode, we can make all kinds of logic. The diode can have a logic array. The logic array is like you have input lines and output lines. You connect them with diode. Then we can make a random logic. This is output. X is this one, fx. So logic array. We can make a logic array using a bunch of diode. Now the MOS device, NMOS. What is NMOS? Is inverter is simple. This is a source, drain. This is drain and source. And what happened is MOS is voltage driven. So voltage goes up high, then this current IDS flow and goes low. So it's an inverter, right? So this is called NMOS. It's N using N channel MOS. CMOS. How about CMOS? CMOS is you combine P channel we write this way, and N channel together. So what's happened is when this voltage is low, since it's P channel, the low voltage is going to turn on this on and turn off this side. Okay, so output becomes high when this is low. When input is high, then NMOS turn on, okay, and this will be off. So this will be low. So basically you have a turn on transistor at the bottom and turn off transistor at the top. So what happened, this on and off timing has to be adjusted very precisely by setting threshold voltage condition for this CMOS. Otherwise, if you turn off this first and you turn on later, turn on this MOS device later, there is some transient problem. Okay, the MOS device fan out, it's all to the gates, which is capacitive. So the MOS device, the problem is switching speed depend on how quick you can charge this capacitor and discharge this capacitor. Okay. So CMOS IDS and input voltage low and high has this kind of characteristic. So when device is low, there's hardly no IDS, the current flowing. Device is high, no current flowing. Current flow only during transition, low to high. Okay, this is quite different from bipolar gate. And what's happened is the CMOS, the biggest advantage is say you have a LSI chip, 1 million gates, lots of gates, and all the gate up and down is switching around, and it's consume the IDS times whatever switching gate. Now, logical design, you can make it possible, like a CPU, to execute one instruction with minimum gate switching. That means n is very small to execute instruction. So this is possible by design to create low power CPU, and ARM is famous for that. Okay, so this is the advantage of CMOS. But compared with bipolar, CMOS gate is generally slow. So in order to overcome they make small size CMOS. Here capacitor decrease. Right now 7 nanometer. This is the gate size. Gate is the MOS device. Gate width. This is the gate width 7, and they are talking about making 3 nanometer and possibly 2 nanometer. I'm not sure if they can make it 2 nanometers. 2 nanometers already it doesn't form N channel or P channel anymore. So whether it's operate like transistor is a question. So even 3 nanometers, if you look at the IBM 3 nanometers test chip, they make MOS gate vertically. Real state is small, 2 nanometer, but within 2 nanometer they build a so-called fin, and most devices kind of made vertically. So I don't know how much it's improved in performance viewpoint, but anyway, 7 nanometer is incredibly small. The bipolar technology came down to somewhere around 38 nanometer, and there is an intrinsic difficulty of making a bipolar smaller, because bipolar actually N-type, P-type, and N-type. So this is the collector, base, and emitter, and this N-type, P-type is all diffused into the silicon chip, and diffusion control is limited. And if you try to make a 7 nanometer bipolar, this is quite a challenge. But CMOS is, the MOS is only surface the surface you can make very small width between drain and source. Okay, so in this case, in this sense, MOS has advantage shrinking the size, and CMOS has an advantage of reducing power. Now, how do you make then other than inverter? Just inverter is boring. So inverter is made this way, right? Now what you do is connect this parallel and serial here. So what's happened is when, oh sorry, this is two different input. When you have A and B, when A is on and B is off, then it won't work, right? Because this is off, so it's always already high. That means it's a NAND gate, right? So in order to switch this gate to get the output low, both has to be high. A and B has to be high, and A and B has to be high. I mean, both this guy is off and this guy will be on. Okay, so that's the way. Disadvantage is CMOS. Number of transistors you use for each gate increase. Okay, so there is a advantage and disadvantage, but the overwhelming advantage for making LSI is CMOS, because power consideration. 1 million gate is a lot of current flowing through the chip. If chip consumes 3 amp, it's almost impossible because it's going to heat up, right? It has to be less than 1 amp, and the process possible to make small geometry. Okay, so that's how the digital circuit is created. Basically, it's create basic logic gate, and the logic gate is created, then any kind of large digital circuit is just combination of them. Okay, so it's quite straightforward. It's logic level, logic element level created. That's why the LSI design, they have a library of logic element, and each logic element is optimized for kind of particular logic, like flip-flop, whatever, and you just put them together to create the entire logic. And if you expand the logic size big, then it's become LSI. So this is how the transistor, diode. There are some others circuit used in various situations, but we will mention that in the next video as analog circuit using transistors and diode and stuff. Okay, let's go to please, if you like, subscribe, and we go take a look at the the circuit on breadboard. It's at the end of lecture I always show the real electronics test board, breadboard, and the signals on the oscilloscope. Okay. Okay, we built a simple transistor logic gate. This is inverter. So this is a transistor here, and it's a left phase. So this is the collector connected to the load resistor to the 5 volt, and LED is cross collector to emitter, because emitter goes to ground, and base in the middle is picked up here, and the base is connected to the switch, and when you press the switch, the base is going high, and the shunt resistor going to the ground is eliminated here because there's no big deal for demonstration. Without that, it works. So what happened is, when you press, LED goes off, right? If you don't press on, it's inverter, so on in the input, output off. Off in the input, output is on. So this is inverter, and we can add diode and make a multiple input, and that's going to make a the NOR gates. We mentioned that in the lecture, right? So let's apply some input. Right now input off. So what's happened? We apply from pulse generator the pulse. What happened? Okay. And this is the ground, right? And we check output. Output is this guy, right? So right now we got input and output. Okay, now if you see this signal level, the rise time is slow. You see this one? 4 times faster. Rise time is slow. And I had to talk about this one. Why? Okay. In the transistor, the old-fashioned TTL, the transistor go into saturation mode. When transistor is saturated, it's create a lot of, for NPN transistor, the hole in the base area. And when you turn it off, all the hole has to be removed. and it's removed by recombination. This recombination speed is very slow, and that's why TTL is generally very slow. So what's happened is they attach Schottky diode from base to collector. And the Schottky diode, what the Schottky diode is, its on voltage is very low, like 200 millivolt. So the collector is clamped to the 200 millivolt below the base, so the transistor never saturate. It's go all the way saturation, only slightly saturate. So turn off speed improved dramatically, and that is called the Schottky transistor. Schottky transistor is used for Schottky logic, and the power you can decrease quite substantially to maintain the same speed pretty much. So low power Schottky is the typical bipolar logic device you use. I don't have a good MOS device here, so I cannot make comparisons, but yes, MOS is also it's operated pretty much same way. NMOS configuration. CMOS is going to be different. You see the rise and the fall time becomes an issue because the output load is a capacitive load, and you have to charge up a capacitor and discharge a capacitor. Okay, that's it.